you'll remember before the midsem, we were looking at how to essentially analyze slow flows. In here, the main thing about these flows is that they're completely dominated by friction. And so one way that we saw first was to just assume the same thing that we assume for static systems, and that is just assume more Coulomb is satisfied. But the more Coulomb theory doesn't give us how the density changes with deformation. And then we talked about another theory called the critical state theory. This has actually been developed in the context of soil mechanics. And in this theory, the basic idea is that you take into account changes in density. So as I mentioned, it takes into account changes in bulk density, but also it also makes sure that the stresses are independent of the relative velocity between particles. And we saw also that the theory is such that you may have compaction or dilation depending on the stress, and at the critical state there is no change in bulk density. And in fact, we also saw that when you are at the critical state, you satisfy the more Coulomb condition. So in a sense, the critical state theory reduces to the more Coulomb theory when you are at the critical state. And in the last class, we did one example. Looks like I'm sharing a wrong. I should be showing some other transfer. Let me just see. There's some mistake here. This was I showed you this last time. I wanted to show something else this time. Okay. Okay. So this was the one that I wanted to show you. And so we saw that these are the postulates. One is that the yield function is a function of the principal normal stresses, sigma 1, sigma 2, sigma 3, and the bulk density. The second thing is the coaxiality condition, that is the principal axes of the stress are collinear with the principal axis of the rate of deformation tensor, where d is just given by this, where v is the velocity and gradient of v is the velocity gradient. And the third condition was that there's a flow rule which says that the principal component of the rate of deformation tensor is related to the principal component of the stress tensor by this equation, where lambda is just some arbitrary constant. So we wanted to look at one example of how to find the critical state. And this is what we did last time, that supposing we are given a function like this, that f is equal to 0 in terms of tau max and sigma m. Now we know tau max and sigma m are directly related to the principal component sigma 1 and sigma 2. We will remember that tau max is just sigma 1 minus sigma 2 divided by 2, and sigma m is equal to sigma 1 plus sigma 2 divided by 2. So essentially, this is a function of the principal stresses, and the density comes in through this sigma c, which has a bulk density in there. So this is in fact a function of sigma 1, sigma 2, and rho v, because it's in 2 dimensions. And so you have f is equal to 0. And in the previous class, we tried to find what is the condition for the critical state given this yield condition. So if we use the flow rule, then we find out that the ratio of del f by del sigma 1 to del f by del sigma 2 is -1. This is for any function f. We have proved this. So at the critical state, this ratio must be equal to -1. And if we write del f by del sigma 1 in terms of tau max and sigma m, then you can see that through the chain rule you will get this. And then we know sigma m is just, this is 1, and this, I mean, this is half, and this is also half, so you get this. And then if you do it for sigma 2, you'll get again the same thing, but now here this is -half, and this is half, so you get minus plus. And so the ratio of these two is equal to -1 at the critical state. But we also know that del f by del tau max is just 1, and we can get del f by del sigma m as this del f by del alpha into del alpha by sigma del sigma m, which is just 1 by sigma c into del f by del alpha. So we have both these derivatives. We want both of these, del f by del tau max and del f by del sigma m. And when we calculate this by using the definition of f, we just get this relationship. Now if we put del f by del sigma 2 equal to this quantity which we have just derived as equal to -1, then you can get del f by del sigma m is equal to 0. And if this is the case, if del sigma by del f by del sigma m is 0, then you get alpha is equal to 1. So basically what it says is, since alpha is just the ratio of the mean stress to this critical stress, so when alpha is 1, you essentially get that sigma m is equal to sigma c, which is a function of only the bulk density. So this is how you would find the critical state for a given yield function. Now what I'd like to do is, I'd like to do one simple example in which I will solve the same problem we did for the Moore Coulomb theory. I'm going to solve exactly that same problem for this critical state theory. That is, what is the flow in a wedge-shaped hopper? So this one is lecture number 21. So let me share my screen again. Okay, so this is, we were doing all this last time. I must say last time I made a mistake while writing this. This should actually be tau max, and this point is sigma c sine of theta. So today is the 20th. Wow, time is going by. 2921, and the lecture is also number 21. Okay, and today my idea is to actually solve the I want to solve for the flow in a wedge-shaped hopper using the critical state theory. So that's my idea. So we want to do slow flow in a wedge-shaped hopper using the critical state theory. And the assumptions are going to be exactly the same as what we had used last time, with only one relaxation. So we have frictionless walls. Let me first just draw the system and then I'll tell you the assumptions. Just to remind you that, we have two walls like this. Okay, maybe I can make this a little longer. And you have some material in here. You can imagine that this is a 2D system and we are looking from the side. So we are not looking in the dimension perpendicular to the screen. Everything is uniform. And we use the cylindrical coordinate system for this, with this as the origin. And let's say this is the midline. Then any point in here we say is at a distance r and at angle theta. And we have taken this whole angle to be theta w. So we assume two things to make stuff easier for us. One is that the walls are frictionless, as we had done for the previous problem. And the second one we assume is radial gravity. That is, the gravity is always in the direction pointing towards the origin. Excuse me. So this is just like in what we did for the Savage. And in here, what we can assume is that v theta is equal to 0, and also that there is no theta dependence. So all derivatives with respect to theta are 0. And let's suppose that we are given that the yield condition is exactly the same as what we did in the example before. So let's suppose that the yield condition is just f is equal to tau max minus sigma c sine of beta into n alpha minus n minus 1 into alpha raised to the power of n divided by n minus 1. So this is a function. So this is exactly what we did last time. And then you know that alpha here is just the mean stress divided by sigma c. So this is something like a dimensionless mean stress. You're dividing by another stress. So this alpha is a dimensionless quantity. And of course, the yield function is f is equal to 0. So this is alpha. And then we know that sigma c is also equal to a1 exponential of minus a2 by rho b. I'm putting a1 by a2 because we're going to get some a at a later stage, so I don't want to get it confused. So here we have already shown in the previous example that for this yield function, since f is equal to 0, you have actually tau max is some function of sigma m. So if you plot tau max versus sigma m, then you can see at very small values of sigma m, you will get essentially a linear curve, and then it will become maximum. And then go to 0. So this has two roots. So when alpha is 1, I'm sorry, there will be when alpha is 0, it is definitely equal to 0. That is, when sigma m is 0, this is 0. But then there's another value of sigma m also when you get this quantity is 0. And that is when n into alpha minus n minus when this is equal to 0. So you can see that this is just when alpha raised to the power of n divided by n minus 1 is equal to n divided by n minus 1. And if you simplify this out, this is just 1 upon n minus 1 is equal to n divided by n minus 1. So the second root where this thing is 0, let's call it as alpha 1, just to be clear, is just equal to n divided by n minus 1 raised to the power of n minus 1. So this is the second root that we get. So this corresponds to alpha 1 times sigma c. And where it is maximum, we have already proved that alpha is equal to 1, so sigma m is equal to sigma c. So this is what the yield function looks like. And this is for a particular value of rho b. As you change rho b, you'll get a different curve. And so you'll have different states. And if you look at the line that is going through this point, you see that when this is sigma c, that means when alpha is equal to 1, sigma m is equal to sigma c. So basically, you have from this equation, when alpha is equal to 1, then this term becomes equal to 1. So when alpha is equal to 1, from the yield condition, we have f is equal to 0, so you have tau max minus sigma c sine beta is equal to 0. And we know sigma c is equal to sigma m, so this gives us tau max divided by sigma m is equal to sine of beta. So this angle is beta, and so this is just the Mohr Coulomb line. So this is what I was saying, that it always reduces to that. So this is the yield function for this. And then we have the coaxiality condition. Now we want to simplify a little bit. So we need to find out what are the okay, I'll come back to this a little later. Coaxiality condition we'll do a little later. So we have coaxiality condition and flow rule. Coaxiality condition means that has the same principal axes, and we'll see how to write that down, and flow rule will give us another relationship. So let's just write down the continuity equation for this case, which is the same as before. But there's only one small change, and that is now we don't take density to be a constant. So we get d by dr of rho b into rvr is equal to 0. And then if we write down the momentum balance equation, then we'll get rho b vr dvr by dr is equal to d sigma rr divided by dr minus sigma rr minus sigma theta plus minus rho b into g. Since the gravity acts in the radial direction, that's why g of r is just g. So these are the two conditions that we have, the two main equations. Now we would like to write down everything else, like what is the coaxiality condition. So now, supposing like we had written for sigma, supposing gamma is the angle between the principal axis and E theta. That is a unit vector that is in the theta direction, which is this. So we are looking at supposing, I'm sorry. Yeah, suppose anyway, suppose this angle, we call it as gamma. So that is the angle between E theta and that. So if gamma is 0, then, and that's what we are going to show, then the principal axis is along E theta. Supposing this is the case, then we can write down our actual values of the deformation tensor, DRR and all, in terms of the principal components as just this. And we had done this for the stress, and exactly the same thing will hold true for So if you look back in your notes, you'll see that we had written sigma RR, sigma theta theta, and sigma R theta, or sigma XX, sigma YY, and sigma XY in this formula. So it doesn't matter what it is, it's all given by this. We can do it exactly the same way. So this is what you get. And really, I mean, I'm writing all this down, but what you find out, if you actually use this expression, then you know that since VR is equal to Vr is only a function of r, and v theta is 0. So then we know that dr theta, which is just given by half. Now this you can look up in any textbook. The formula for what is dr theta in cylindrical coordinates. Now you see v theta is 0, so this term is 0. Vr doesn't depend on theta, so this term is 0. Second term is 0. And again, v theta is equal to 0, so this term is 0. So basically what I wanted to do, it's a bit long, but what I wanted to show you is that essentially dr theta is 0. So that means if dr theta is 0, then this implies that essentially the angle between the principal axis and E theta is equal to 0. So gamma is equal to 0. So that means r and theta are the principal axes. And so this gives us, and here I'm writing it down as d1 is equal to d theta theta. That is, the major principal axis is in the theta direction, and the minor principal axis is in the r direction. And due to coaxiality, since the directions are the same, since the principal axes are collinear, so then you also get that the principal stress must be equal to sigma theta theta. It must be in the same direction, and sigma 2 must be equal to sigma r. So this is what the coaxiality condition gives us, that both of these principal axes act in the same direction. I mean, both of these principal components act in the same direction. Now let's just look at the flow rule.
Sir, I apologize to disturb, but I have one thing to ask.
Sure, go ahead.
Yes, so in the previous derivation, we have assumed that the g, the acceleration due to gravity in the radial direction, is constant.
Yeah.
So it is possible when the wage angle is too small, right?
No, this is just a hypothetical thing. In reality, it will always depend on g into r cos theta. But you're right, if theta is very small, then cos theta is almost equal to 1. You're right. Why?
Yes, sir, because the variation along the theta direction will be so small to that we can ignore it.
Yeah. But you know, we are sort of trying to do this as just as an exercise. So we are saying that it's, you know, for all angles, we are always going to take g to be radially directed. So that means, you know, we are not bothered about the cos theta part. Of course,
Okay.
if you wanted to do an experiment, then it's difficult. But if you want to do computations, then it's very easy to do these type of computations where you put the radial gravity and so forth. But
Yes.
you're right. If you want to do an experiment, then you should do an experiment with a hopper whose angle is very small, so that you know the maximum value of cos theta doesn't deviate much from 1.
Yes. Okay. Thank you, sir.
Very good. Good question. Yeah. Please stop me and ask questions. Then I know that somebody is there on the other side. Otherwise, I feel like I'm just talking to the screen. Okay. So now, see, now again we'll look at the flow rule. Now we are not at the critical state, right? So what does the flow rule tell us? The flow rule, if you remember, is just that, sorry. The flow rule says that di, or why not just write it as this, that d1 is equal to lambda into del f by del sigma 1, and d2 is equal to lambda del f by del sigma 2. And so this actually gives us that d1 by d2 is just equal to del f by del sigma 1 divided by del f by del sigma 2. Maybe I should have done a little bit more on the thing, because since we know that VR and all are 0, we can easily see that d theta theta now. So d1 we have said is d theta theta, and that is also known, and that is given by VR divided by R, and d2 is equal to drr, which is just equal to del VR by del R. So both these quantities are actually known quantities in terms of the velocity vector. So now if we write down, if we simplify this, we know also that, and this we have seen from this geometry before, that we can write down del of tau max by del sigma m as just equal to minus del f by del sigma m divided by del f by del tau max. Okay. Now I'm going the other way around in a sense, because I know what is del f by del sigma 1. So I want to put these in terms of sigma 1 and sigma 2. So this is just equal to minus of del f by del sigma 1 into del sigma 1 times del sigma m plus del f by del sigma 2 into del sigma 2 by del sigma m. So that is del f by del sigma m in terms of sigma 1 and sigma 2, and then divide by del f by del sigma 1 into del sigma 1 by del tau max plus del f by del sigma 2 into del sigma 2. And if we simplify this, this is just minus del f by del sigma 1 plus del f by del sigma 2 divided by del f by del sigma 1 minus del f. And now if I divide throughout by del f by del sigma 2, then I can use this expression, and what I will get is that this is simply equal to minus of d1 by d2 plus 1 divided by d1 by d2 minus 1. So this is what you get. So I'm dividing top and bottom by del f by del sigma 2, then I'll get the ratio of these two, and then I can use this expression to substitute in terms of this. So I did a little bit of algebra, and you can try it out yourself. And what I've got is that now that del of tau max by del sigma m is just equal to I can multiply throughout by d2, and so this is just minus d1 plus d2 divided by this is what I get. So, what is different from what we did in the example? Well, if we wanted to do in the example, we would have also reached this stage. But at the critical state, your density is constant. If rho b is constant, then that means that divergence of v is equal to 0. And that means that d1 plus d2, which is equal to the trace of d, which is equal to the trace of the gradient of v, which is equal to divergence of v, is equal to 0. So we'll get back the result from the original, from the example that we did last time. If density is constant, then you'll essentially get d1 plus d2 is 0. And that's what we had said, that if we go back to this example, then we see that when del of tau max by del sigma m is 0, that is at the maximum point, we are at the critical state. So this is what it is. But we are not in this, we don't assume critical state. So that is why this slope is given by this. So we are at some point which is not the critical state. So the sum of d1 plus d2 need not be equal to 0. Now, if you want to calculate, and we have done this already, we know that del tau max by del sigma m we have calculated. This just turns out to be sigma sine beta we have, I think just up there we have done this. This is just sigma c sine beta into n minus n into alpha raised to the power of 1 upon n minus 1. So we did this. We have done this derivation before. So, if we write so this divided by sigma c, of course. So if we simplify this, we see that this is just equal to sine of beta. So that's just n into sine beta into 1 minus alpha. So if I want to write it in terms of sigma m, just to be clear, so sigma m by sigma c divided by n. So this is what it is. And now we have a nice relationship between these two quantities, and we see that we get n sine of beta into 1 minus sigma m by sigma c raised to the power of 1 upon n minus 1 is equal to d theta theta plus drr divided by d theta theta minus dr. And if you substitute for what is d theta, theta, and drr, so this is just equal to Vr divided by r plus del Vr by del r divided by Vr by r minus. So this is what you get. So you get a relation. Yeah.
Sir, there is a negative sign.
Missing, right here. This is a minus sign here. You're right. So this is what you get, and so you can write. I'm going to write this one more time. So this is one equation. That relates the velocity and the stresses. So we have, like, if I go back, let me just number the equations. So let's call this as the first equation. Let's say this is 1. Okay. And of course, the momentum balance is equation number 2. I'm just counting how many equations we have and whether they are enough. And let's call this equation as equation number 3. And so, and then we have and this equation is equation 4. Okay. So of course, we know that sigma 1 is equal to sigma theta theta, and sigma 2 is equal to sigma rr. So if you actually see the unknown quantities in terms of the original variables, they are Vr, sigma theta theta, sigma rr, and the density. So there are 4 unknowns and 4 equations. So this implies that the problem can be solved. And we know we can just get straight off the solution when, if it is at the critical state, we have already shown that alpha is equal to 1, or basically sigma m is equal to sigma c. So if sigma m is equal to sigma c or alpha is equal to 1, so then equation 3 simply gives you that this whole thing is, the left hand side becomes, if sigma m is equal to sigma c, then the left hand side is 0. And so you will get that Vr by r plus dVr by dr is equal to 0. So your continuity equation reduces to this. So this implies from the continuity equation, of course, that rho b is a constant. From this equation. From this equation, if rho b is a constant, then you will get exactly this, what we have written down. And then equation 4 simply reduces to tau max is equal to sigma m sine beta, which is the Mohr Coulomb condition. So if we were at the critical state everywhere, so then this is exactly the earlier problem, reduces to the earlier problem which we solved at the critical state. But supposing it is not at the critical state, then we have to solve these 4 equations simultaneously, and we should be able to get a solution, but you need a numerical solution to this. So we will just stop at this stage and assume that if we need to, we can get a numerical solution. It's also possible, say if we assume that, let's say, this is also something that we can do. So let's say density is nearly constant, so you just say it's 1 plus some function like this. Let's say it's increasing with radius. So if we assume something like this, then you can get an approximate solution, and so that it gives you the first deviations from the Mohr Coulomb. So that is also possible, and maybe I will upload that derivation on the Moodle site for you to have a look at. But the main thing is I wanted to just illustrate by doing this that we can actually solve this problem. Okay, so now, bins and hoppers, like what we have been looking at, they are used quite widely. Very, very commonly used. And many of them have a design that's something like this. That they will have either a wedge at the bottom or a conical section, depending on whether it's got a cylindrical or a rectangular cross section. So this could be either a wedge, like what you have been, or a cone. And the desirable sort of mass flow rate is to have what they call mass flow, in which the particles flow in with streamlines that look like this. So there is no stagnant zone at all. So this is called mass flow, and usually this depends on what is the flow properties of the material, and also on the angle. So this angle should be large enough that there is no stagnant zone formed. But even in these types of cases, there may be some there may be some sorts of situations where material is sticky or something like this, in which case, there is no uniform flow, but you may get actually some regions that just remain stagnant. Like in these regions, it may just be stagnant, and then the flow occurs only in a small part of the hopper. So this is not usually desirable, and this is called funnel flow. And it creates large stagnant zones. And in most industrial processes, this type of stagnant zone is highly undesirable, because what happens is invariably the particles tend to stick together, and then it becomes like a solid mass which you can't get rid of. You have to go inside and chip it out and so forth. So you would like to have mass flow. So you would like to have, first of all, the hopper angle. If you see, theta must be small enough to prevent stagnant zones and ensure mass flow. And so what is this? Theta will depend on both angle of internal friction of the material, and it will also depend on the wall friction coefficient. And quite detailed methods are available in the literature, mostly empirical, to determine what this angle should be. And then the second point is that this is the hopper angle, and the hopper exit diameter, it should be large enough to prevent arch formation. And in this, what happens is that, let's say if you just look only at the exit, the particles, they get some kind of arch that forms. And these particles are usually highly resistant to compression. So they're very stiff particles. So this just forms like a impenetrable boundary. And the flow just stops. Now you've seen arches, where in architecture, where they put stones in a nice angle, and that can withstand a huge amount of force. So, even in practical situations, if you sometimes have sticky particles or arch forms, and then it becomes very difficult to generate the flow again. People do all sorts of things, but I have seen in industry, that if you go and see one of those metal hoppers, what they will do is if an arch forms, then there's a guy with a huge hammer who will come and just hit the side of the cone so that the arch breaks and the flow starts again. So if you go to industry, very often you will find some of these feed hoppers with lots of bang marks on the outside. There are of course many other better solutions that are there. They will put some kinds of uh, disruptors to disrupt the formation of an arch, or they will have some smooth walls by putting coatings and so forth to prevent this. So again, these are very interesting areas, and one can go and read about this. I just want to point to you that these are the issues which you have to take into account when if you are designing a hopper. And the final thing I'd like to say is that one of the important things is calculation of the mass flow rate. So if you want to find out how much material is going to come out, well, I'm going to do this in the next class, but what is nice is that if the height h is more than about 2.5 times d0, and if the diameter of the hopper d is also larger than about 2.5 times d0, then the mass flow rate is independent of h and d. Okay, so if I just draw it over here, this is d0, this is d, and this is h. So in fact, what it turns out is that if you are in most practical situations, of course, where these things are always satisfied, what I wrote down, then just the size of the orifice determines what will be the mass flow rate. And that I'll do in the next class, which is just an empirical expression for the mass flow rate. So I'll stop at this stage, and I'll meet you tomorrow morning in the class.
Hello, sir.
Yes, please.
Sir, one more thing to ask.
Yeah, go ahead.
Yes, sir. So the in our previous derivation, we have assumed that g is varying along the radial direction only, right?
No, g is constant. G is just constant, but it acts in the direction of the radius.
Okay, okay, okay.
So it is like, if you imagine, say if you had something like centrifugal force, then you know that force acts only in the radial direction. You can imagine some force like that you have a system which generates a force that is only in the radial direction. So, if you wanted to maybe do an experiment, you could keep this cone with the cone outlet pointing in at the higher radius, and then you spin it around. Then the gravity will act only in the, well, no. If you keep it like this, then with the cone thing at the center, then the gravity will act in the opposite direction to what we want, but it will act only in the radial direction. So one can think of physical situations where your force is purely radial. And one simple example is, if you have centrifugal motion, that is, if something is rotating, then the centrifugal force is purely radial. But what I'm saying is that this is just an approximation that I've made not I, but even previous researchers have made, just to simplify the analysis. So, you you can actually get to a final result. But you can solve the same problem, exactly what we have done, with the normal gravity, that is gravity acting downward rather than in the radial direction. And you will get a solution, but maybe you have to do a more detailed analysis, or you have to do a numerical simulation of the equations and so forth. Because the minute you say that it's not radial, gravity is not radial, then you will see that sigma theta theta and sigma RR are no longer the principal stresses. So then, and those things will vary in different places. And so, you'll get a really complicated solution. So you'll remember the equations I wrote down for stress distribution in a bin. So you have to go through this complex thing to find out what are the principal stresses at each point. Then the ratio of those principal stresses equal to K. So then you will get a nice long equation, and then to solve it, you have to go to the computer.
Yes, sir. Yes, sir. Is it possible in the granular flows that the gravity in the top side of hopper and the bottom side of hopper varies along that distance?
No, gravity is a constant force, no?
No. Like I mean, no gravity, but density. Sorry.
Oh, of course, density varies. Usually what will happen is the density will be more near the top. And then if the material is flowing, then the material in the flowing region where the velocities are higher, like let's say if you come to these kinds of places over here, if you come to these regions where the velocity is quite high, then the density will become low. So you'll have high density and then lower density. Yes, but these density changes are small. The main problem is that small changes in density can make a huge difference in the frictional force and the stress and all that. So those things have to be taken into account.
Thank you, sir.
Anything else?
Sir,
Yeah, go ahead.
as the Hopper angle decreases, the reason for getting stagnant region will increase now.
As the Hopper angle decreases, then what happens?
The reason then it will become a rectangular bin.
Ah,
Then the stagnant region
well,
will increase.
it's like, it's not exactly. I mean, it'll be like, supposing you keep. The way I can say it is, let's say if I draw it, let's say this is one. This is one. Supposing I want to draw something with a smaller
So
angle,
screen is
I'll share the screen one second. No, not this. This. Okay, so let's say, for example, if I'm drawing this, so this is, let's say, the upper part of the hopper. That remains the same. And then let's say I have one angle which is over here, and that is d0. So this is one angle of theta. Now if I want to reduce the angle, then I will go to this. But I want to keep d0 the same. So now I'll have this as my new. So I'll draw this again. So I'll make this long. So this outlet diameter d0 should remain the same. And then you are changing the angle. So let's say, for example, I can make this as an angle which is smaller. And so as you go on reducing the angle, you will get a longer and longer bin, but it will never become a rectangular bin because I'm always going to keep this as my outlet. Is this okay?
Yes, sir. Now I got it.
But of course, there are some people who will just simply, when materials, you don't want to bother too much about the stagnant material, then you can actually have this type of system where now the material will remain stagnant over there and then the flow will occur like this. So that is also possible. So this is usually called a bin. So, you can have material flowing out of a bin. And if your material, you don't care whether there's a stagnant zone or not, then you can use this. So this is much easier to construct. But if you have sticky materials and if you have materials in which you don't want a stagnant zone to form, then you have to go for this.
Okay, sir. Thank you, sir.
Bye-bye.